the production routes are from natural gas. We don't have clean hydrogen or clean ammonia in this case. The comparisons are for gray cases. So all the feedstocks are hydrogen. For ammonia, methanol, dimethyl ether, the feedstock is hydrogen. That's why we need to first produce hydrogen. The LNG production energy consumption is 6.7 megajoule, but ammonia production is 28.6 megajoule. So which is due to the higher energy consumption in the cryogenic air separation and also Haber-Bosch process. When we compare the BOG emissions, you see the highest one is in liquid hydrogen at the bottom, but for LNG 3.6%, the voyage duration is 30 days, which is around transporting the hydrogen or ammonia from Qatar to Japan. When you see the boil-off gas during transportation of hydrogen, you see 31.8%. Which means that if we don't recover the BOG, 31.8% of hydrogen will be vanished during the ocean transportation. And most of the time, the currents they have BOG venting to the environment. If it is LNG, it is methane, and methane venting will have a global warming effect. But if it's hydrogen, no direct global warming effect, but you lose 30% if you don't have any precautions during the transportation. We have similar trends for on-land storage, 3 days on-land storage, 2% is lost. For some cases, for regasification, if needed, for ammonia and hydrogen, there will be additional losses in those cases. So this is another representation of the voyage length versus total delivered energy. Okay, most of the time, we show total delivered mass. But if we carry the product as an energy carrier, we should care about the delivered energy. That's why we convert them to delivered energy. If there is, we compare two cases, 0% BOG recovery and 90% BOG recovery. What does BOG recovery means? Either you use in the ship for propulsion in the engines, or you reliquefy on board. If you don't reliquefy or use on board, after 90 days, there is no hydrogen remaining in the storage tanks. All of them evaporated. For liquid ammonia, we are lucky that because of the storage temperature is -34, we don't have much losses. Here, one of the key criteria, keep in mind, we have fixed volume of the ship, ocean tanker. That's why delivered energy contents in the beginning are different. And it starts with higher energy content for liquid DME and LNG because of their energy densities and also normal densities. If we have the utilization of BOG, then the reduction in the energy, delivered energy, is smaller in the hydrogen compared to non-utilized case, but still it has a lowest delivered energy among the others. Okay, now we assess the BOGs. We know how much it is lost during each phase of the supply chain. We can continue with the techno-economic assessment and the life cycle assessment. First, techno-economic assessment. We run the techno-economic assessment for the same energy carriers, 5 of them. But here, what we have considered, 2 additional cost parameters: social cost of carbon and boil-off gas cost. So this lost amount, boil-off gas, 30% in hydrogen or 22% for ammonia, we consider it as a cost because it is an unavoidable cost. And the emissions from the production, from the storage, and from the BOGs, we consider them as well as the social cost of carbon parameter, where we assign a cost to carbon dioxide or carbon equivalency, and then we try to calculate the additional cost. In the transportation phase, we consider all port charges, maintenance, insurances even, and one of the main elements is the fuel cost, because the ocean tankers are driven by mainly HFO, heavy fuel oil, which is a carbon-containing fuel and which will emit lots of emissions. Those emissions will be also taken into account in the social cost of carbon, That's why there will be changes in the cost values. Sailing time is 13 days in the base case. No reliquefaction is considered on board, and BOG is vented because we are quantifying the cost of BOG in this case. And all tanks are spherical. So first, I will show the transportation phase cost only, and then I will show the total cost. What is the transportation cost? Only this phase. But we have also production cost. Production cost of LNG will be lower, of course, because we don't have the additional step of hydrogen production. But transportation cost will only consider the voyage during the ocean transportation. So in this case, we compared per unit energy and per unit kilogram. Again, why do we separate them? Do you use this product as an energy carrier in the end use for power generation, or do you use it as a feedstock for petrochemical industry? Ammonia can be used as a fertilizer or for other urea production, but it can be also used for power generation. As you can see here, the transportation cost per gigajoule highest for liquid hydrogen, and the breakdown shows that the capital cost is, let's say, reasonable. Operating cost is also contributing around $0.5 per gigajoule, but the main cost comes from the BOG cost, which was unavoidable if you don't have any onboard BOG recovery option. It goes up to $3.5 per each gigajoule. A similar maximum trend is observed in the per kilogram case, but when it goes per kilogram, liquid ammonia has lower cost of transportation than LNG, less BOGs. But for a gigajoule case, because of the lower heating value, lower heating value, we have a bit higher than the LNG and methanol, around $1 per gigajoule. They are still the transportation costs, not the total costs. We also show them per unit volume in case people are interested in per unit volume. Ammonia is $13.87 per meter cube, which is lower than the LNG. When we consider the ship capacity, it has also an effect on the total cost. Higher ship capacities are better. We have lower overall ocean transportation cost. Mainly, the current ships are around 160,000 meter cube. This is the base case we have considered. But there are now bigger ships with 250,000 meter cube. Okay, this is one of my favorite slides. So if you want to transport these energy carriers to different countries, but it was produced from Qatar, and the production route is gray, and we consider the existing scenarios, we even consider the tankers are modified based on these energy carriers. If it is ammonia tanker, it is maybe less insulation. LNG tanker, more insulation. Hydrogen tanker, more insulation. Here you see that if you transport to, let's say, ammonia to China, $0.92 per gigajoule, but which is higher than transporting DME to Japan, to India, sorry, hydrogen to India, which is 0.8. So it means if you want to transport an energy carrier for power or for energy purposes, you can transport liquid hydrogen to India, which is more feasible, but you can transport liquid ammonia to China. Why? Because of the distance mainly. India is closer, less than 3,000 or 4,000 kilometers, but China and Japan longer duration. This also supports the previous presentations that the duration is key in the storage and the overall transportation costs. But hydrogen is transporting hydrogen to Japan or China around $2.74 per gigajoule from Qatar. They are all in liquid form. Liquefaction is included. Okay, what happens if we consider the environmental cost of CO2 equivalent included in the production and also transportation phases? What does it mean? In each phase, ammonia production, we have normally gray ammonia, steam methane reforming. There's lots of CO2 emissions, around 2 kilogram per each kilogram of CO2. When we consider them in the production and also transportation, if we have the BOGs, boil off gas, which is emitted to environment, they will have also some greenhouse effect in case of energy and other carbon ones, not ammonia and hydrogen. Plus we have HFO tankers, which also releases any carbon emissions during the transportation. Here you see the production emissions are increasing a lot for the production of ammonia because it's gray. Same for the hydrogen because it's gray hydrogen production. We have lots of reforming processes happening where CO2 is emitted, and also liquefaction processes consuming electricity, and electricity comes from natural gas, not from renewables. Again, this is the dirtiest solution, and everything comes from gray. When you consider the total cost of hydrogen with environmental cost included, $1.6 per kilogram. But if you consider per gigajoule, we have around $15 per gigajoule. And this is another representation of social cost of carbon. We assign a value to the carbon dioxide, dollar per ton, 13 or 46 or 137. The highest increase mainly in the LNG case. Here, the production is 5.86, transportation cost in the base case 0.74, but if you include the social cost of carbon, production emissions remains 26% higher, but transportation emissions are significantly higher because of methane BOG, which is released to environment, which causes additional cost of carbon dioxide or GHG equivalent. So in this case, transporting ammonia becomes even better per kilogram because social cost of carbon included, and during ocean transportation of ammonia, we don't have any GHGs. Okay, now economic side we are finishing. Now we will focus on the environmental sides. So environmental impacts will be slightly different than the economic results, mostly controversial. We consider the same energy carriers: LNG, ammonia, methanol, dimethyl ether, and hydrogen, all of them liquefied, produced. In this case, we will have different sensitivity analysis of producing these energy carriers from other renewables as well, loading, and then ocean transportation. Here we said HFO and LNG can be also utilized. There are LNG fueled tankers recently. And finally, we utilize them in an internal combustion engine. So this is the complete supply chain, because during the utilization phase, you will see the carbon containing fuels will have drawbacks. Also in the ammonia case, we may have some NOx drawbacks. The methodology for you just to make it clear, we use GREET software developed by Argonne National Library. We transport these gases from natural gas field to the production field. And then the renewable scenario, liquefaction of hydrogen is included, and the source of electricity is natural gas, okay, not renewables. And GHG emissions per unit mass and unit energy is shown. And we have also shown the NOx and SOx emissions. And the emissions generated due to BOG is also accounted for in the GHG emissions. So here, the boil-off gas emissions, all the routes are from natural gas at the moment, and it's driven from natural gas-based ammonia, or methanol, or DME, or hydrogen production. We transport with HFO tanker 20,000 miles, and we utilize an internal combustion engine. When you consider all these steps, what are the NOx and SOx emissions? The production of NOx emissions from ammonia is also significant utilization. These are all per megajoule, milligram per megajoule. So they are normalized. So it means we can compare them fairly. Transportation, during the ocean transportation, we have 34.9 milligram of NOx emissions. And here, what it emphasizes that if we still use the gray ammonia production, it is also emitting NOx in the beginning. Even you try to reduce the NOx in the utilization phase in the internal combustion engine, we need to also decrease the production. Has the lowest overall here, utilization 8.6 on the NOx, and the production 30.65 milligram per megajoule of NOx. Okay, now we have compared different production routes of ammonia when we consider steam methane reforming plus an Haber-Bosch process with CCS, carbon capture, wind electrolysis based hydrogen, and then ammonia, PV electrolysis, and concentrated light based photoelectrochemical. And when we include the storage and the loading, we consider the GHGs, leakage, and BOGs as well. So in this case, the emission profiles per each kilogram of ammonia. 0 means there's no ocean transportation. When we start transporting it, there will be also more emissions. So in the base case, if during the production of liquid ammonia from natural gas without CCS, carbon capture, 2.24 kilogram CO2 equivalent per kilogram of ammonia. But when you include the transportation, it increases to 2.42 after 20,000 miles. The lowest one is in wind, liquefied ammonia production from wind. In the base case, it was 0.47 kilogram CO2 per kilogram of ammonia, and it increased to 0.65. And even if you produce clean ammonia in one region, you need to transport it to overseas using HFO tankers, which will add additional environmental burdens to the complete supply chain. Okay, this one is a similar representation but showing the breakdowns. The main emissions come from the productions, the blue ones, and the transportation emissions, the orange ones. Utilization emissions of GHG is minimal compared to production and transportation. So it means we need to focus on cleaner production pathways of ammonia and other energy carriers. Another representation, but this one is per megajoule, kilogram per megajoule. So the starting point in the production, and when we start to transport, for example, the green one, ammonia produced from PV electrolysis, it emits and it's increasing to 60 grams per megajoule of fuel. Here you see the gray one, green, which is ammonia with carbon capture. Even when we have the carbon capture, it has still the highest emission profile per megajoule of fuel. And the blue ammonia is still higher than the methanol and DME. Okay, this is also the summary slide, final summary slide of the LCA. So on the left side, megajoule of fuel. On the right side, kilogram of fuel per unit mass and per unit energy. When you see the per megajoule, hydrogens are in a good range. Grams CO2 per megajoule. We have around 40 and 60, with even natural gas reforming with CCS, 50 gram CO2 equivalent per megajoule. But when we transport it into when we convert it into kilogram, hydrogens lose here because of their density. So almost 6 kilogram of CO2 is emitted per each kilogram of hydrogen, and mainly it comes from production. You see the transportation emissions also shown in the breakdown, but utilization emissions are minimal for carbon-free energy carriers, hydrogen and ammonia. But when you see the LNG, DME, methanol, you see they are almost same with the, even though we have high emissions in the production phase of ammonia, they are almost same in the complete supply chain. For example, methanol produced from natural gas, when you consider the utilization in the engine, it goes up to 100 grams per megajoule. So which shows us the importance of complete supply chain analysis. When you consider the utilization as well, you end up with lots of emissions. So still ammonia is cleaner than even methanol produced from biomass in terms of megajoule. And when you consider the per kilogram, it is even cleaner here. So to conclude, ammonia has a lower cost per unit mass in terms of kilogram, but we have lower heating value. The energy density is lower. That's why we lose some in the transportation. But when you consider the social cost of carbon, the BOGs emitted during the LNG over ocean transportation, ammonia is still favored even for the transportation phase. And the energy of natural gas can be converted into other liquefied energy carriers, which are mainly carbon-free ones, but their feasibility will depend on the distance to be taken through the ocean transportation. If the social cost of carbon is around $137 per ton, then the transportation cost of LNG increases more than double. And it means that if there be any future carbon tax or carbon credit implementation, the LNG will suffer and it will favor carbon-free ammonia or hydrogen. And transportation costs of those energy carriers are higher for LNG in this case if the social cost of carbon is higher, $1.68 per gigajoule. And the emissions for steam methane reforming based Haber-Bosch without carbon capture, we have around 2.24 kilogram of CO2. But if you include the carbon capture, it only reduces 24%. We don't reduce 100% in the complete supply chain because there are other phases of ocean transportation and utilization. The lowest CO2 emission was observed in the wind-based ammonia production. So this shows that direct utilization of ammonia either in the engines or in the fuel cells will be quite beneficial to reduce the overall emissions. And finally, producing exporting natural gas as methanol and DME is an option, but if we use them in internal combustion engines, there are significant carbon emissions and GHG emissions. So it means we need to find ways to utilize them, even they are carbon-containing fuels, in a cleaner way, such as not combusting, but maybe using in the fuel cell or capturing the carbon dioxide on the spot. I acknowledge the support of my research team. They all contributed to this work. Thank you very much for your listening and open to any questions.
And thanks, Joseph. And any questions? Okay.
Yeah, thank you for this interesting talk. And I think, I have listened to so many people talking about combusting ammonia as a zero carbon fuel. And I think you said this a bit, I wouldn't say right, but differently. So my question is, in the environmental costs, do you consider land use? Is that the difference between photovoltaic generation and wind generation, or why is that? And the other question is, there's greenhouse gas influences, of course, of methane and N2O, and there's also indirect effects of hydrogen leaks, which catch the OH in the atmosphere and also have some balance on the CO on the climate. And so, are these included, or is it too hard?
Thank you very much. For the land use, we didn't consider the land use because social cost of carbon, only carbon GHG emissions. So N2O is a GHG, but NOx is not GHG, so it is not included. For hydrogen, since it is indirect GHG, we didn't also consider them. We just leak hydrogen as is, but the leaks, the BOGs was high for the hydrogen case, but for methane, it was directly considered because of CH4. What was the last one? H2 radical, yeah. So H2 may have an indirect effect, which needs to be additionally calculated and implemented. But in this one, we didn't calculate.
And other questions?
Yeah, similar as Katharina said, I think you put a couple of things straight. And however, I actually have a question about your assumptions on the hydrogen transport, not on the ammonia. And I might have missed that, but I was a little bit surprised to see two things. The first one is that the capital cost of your hydrogen ships for the liquid hydrogen, at least to me, seemed rather low.
Conservative, yeah.
Very conservative. And then I was wondering, what kind of assumptions did you make in terms of ship size? Because in our techno-economic assessment of hydrogen ships, even taking the IEA numbers that are probably potentially available for liquid hydrogen in 2050, I was not aware that you can transport that much hydrogen on a ship.
So first, ships are fixed 160,000 meter cube in all assessments. So we use existing LNG tankers as a base case, then we modify them. The numbers, which numbers do we modify? For example, we modify the heat transfer value of the tankers, and we increase the tanker costs as well for the liquid hydrogen. If you refer to numbers in the paper, for example, we have liquid hydrogen tanker costs higher than the LNG costs, but they were taken from several references. We modified them. So there is also capacity for 250,000 meter cube. In Qatari fleet, we have lots of 160 ocean tankers. So in terms of capacity, we don't consider the limitation, and we think that it will be available, but these costs are normalized, and they don't refer to levelized cost of hydrogen first. They are normalized for each phase, operation, production, and then utilization, and then we add them up. So if you refer to also cost of hydrogen, which is being low, it is not the levelized cost.
I may just follow up on this. So, but I do understand it correctly that in fact that all the other carriers are basically available. You have ships that can transport DME, that can transport LNG, transport ammonia, but ships of that size for hydrogen are not available, right?
But
so there's the highest uncertainty in terms of cost would be on the hydrogen, right?
Yeah, correct. This is right. For ammonia, we have already ships. For LNG, we have ships. Methanol also being transported. DME is not exactly transported, but it is similar to maybe methanol. But LNG, the hydrogen ships will be an improved version of LNG ships. We are also working on modifications on an existing LNG ship to retrofit to hydrogen. One of our students working on it. There will be, of course, lots of uncertainties, lots of insulation layers, but we may have considered, as you said, the uncertainty of the hydrogen tanker cost. Maybe it will change the picture, but it is still highest.
Okay. Okay, thanks. And other questions? Okay.
So another energy carrier is kind of speculated upon, which is using metals as energy carriers. So did you consider that, you know, there's maybe a usage in power generation and so on? And of course, you would transport something, you know, solid, which is also done. And would you include that in your techno-economic?
Metals or metal hydrides?
Metals.
Metals.
Not metal, you know, something like there are people in different countries using, let's say, iron, aluminum, magnesium, all these kind of things in redox.
Redox experiment. Yeah, redox.
So Eindhoven has a pilot plant in Netherlands, and so that's another option which kind of seems to be arising, but we don't know too much about large-scale usage yet.
Yeah.
Maybe that's an interesting point to consider for future study.
Yeah, exactly. It's a good point. We have never considered the metals to be transported, but it's also a good point when you have a lower cost of electricity, such as Qatar, where you produce from natural gas. There is also Qatar steel and aluminium production facilities, which can be converted into low-cost energy transport as well. A good suggestion. Maybe we will consider in the future.
Okay. And more questions? Oh.
Well, thank you very much for your presentation. My question was related to the upstream side. Going back to the methane emissions, did you consider any fugitive emissions of methane for
Yes.
natural gas production and extractions, and how large are they in terms of supply chain?
Yeah, we have considered the fugitive emissions as well, and we considered a fixed value, for example, 0.17% for hydrogen in the transportation phase. Each of them is available on the paper, but we have considered a ratio, a fixed ratio taken from the reports, industrial reports.
But I meant from natural gas extraction.
And natural gas extraction is very, and during production, for each phase, production, utilization, transportation, we considered leaks and leaks, including the fugitive emissions and BOGs.
Thank you.
You're welcome.
Okay.
Thank
And
you.
other question? Last question. Okay. Okay, I have one question because I found that the ammonia production from the PV is the cost for that is much larger than that from the wind. It is based on the data in your countries, right?
From wind?
Yeah, I found that in the page of 24, the ammonia production from PV, solar PV, is much higher than that from the wind.
Yes.
Yeah.
So the PV is the cost? We didn't consider the cost.
That is in
Emissions?
the 24, the page 24. That is the
there's emissions.
emission. Yeah.
Not the cost. We didn't consider the cost for the
Yes.
renewables. Emissions are lowest for the wind because wind electricity has also lowest emission profile compared to PV. That's the main driving force of the overall lower emission in the ammonia production as well. And even in any production of ammonia from wind will be lowest compared to PV.
Okay, thank you.
You're welcome.
Okay, thanks Yusuf for the interesting presentation. And we have one okay, Carl. Okay. And the last presentation in this session is the invited lecture from Tajada. And the title is Environmental Life Cycle Costing Conventional and Plasma-Based Distributed Ammonia Supply. Okay, welcome, Jos.
Laser, no? Laser, no laser? You can use the mouse. The touchpad. This laser will absorb by the screen. Okay.
Let's wait for about 7 minutes. Okay. I didn't notice the time here. Yeah.
Mr. Me? 35. Yes. And you have a 24 seconds. Okay.
Hello. I think we can start now. So today I would like to share some results of this collaboration with Professor Volker Hessel from the University of Adelaide, in which we basically are trying to find ways to promote the production of ammonia using emerging technologies like plasma. This is because previous techno-economic analysis have demonstrated that producing in these emerging technologies is much more expensive than the conventional Haber-Bosch process. Many times we try to highlight that the ability of producing on smaller scales using plasma or electrolysis can avoid some problems related to the centralization of the tradition. Besides the high ecological footprint, of course, because transporting from one continent to another continent, and the supply disruption related issues like the price volatility and issues, and that have made, for example, 2-3 years ago after COVID and due to the container shortage, we have increased double or 3 times the price of ammonia in America. And during that time, especially in South America, started to think or to consider the local production of ammonia, considering the new technologies to avoid these problems. However, currently in our market, all these ideas have been become less interesting. And for that reason, we need to focus on more reliable, more stable variables like the environmental benefits, because we can have over the time a reduction of emissions, but we need to show these environmental benefits in a more understandable value, like a monetary value. So for that reason, we try to internalize these environmental impacts in the economic analysis of different ammonia pathways beyond the factory gate. That is, considering, besides the impacts of the production of feedstocks, also the transportation and product credits in the distributed plants to promote the adoption of plasma technology. So why plasma? We started this, we have already discussed these days. We try to replace the main parts of the traditional steam methane reforming and Haber-Bosch process, the hydrogen production, replacing using electrolysis. For many years, this idea has been tried to be developed. Another recent solution is the inclusion of a high temperature plasma reactor for methane pyrolysis that also use natural gas and electricity, but this the byproduct is solid carbon black, that is an interesting co-product. But these two technologies have not been massively implemented because the high technology cost and also because the high cost of renewable. That is the main purpose of this kind of alternatives. But recently we know that with the reduction of the solar and wind electricity, the price of this kind of so the production of green hydrogen can be possible by the 2030, opening the door to the production of green ammonia. However, this plant configuration is not yet the perfect solution for using energies, mainly because the thermal inertia that we previously discussed. So we doesn't interface with the intermittency of the renewable energies. So we propose to implement a synthesis that is working at ambient conditions. There is a low pressure, so atmospheric pressure and low temperature, and its rapid ramp can stop and start the production immediately, and it's very simple. It's a simple reactor, non-expensive materials. But yes, the main issue nowadays, I the beginning said, was more expensive in this kind of reactor because they love energy efficiency, so needs a lot of electricity. So how we try to reduce this gap in the cost of production? So we try to internalize the environmental benefits of using this kind of technology. By technology, we calculate the production cost and the sell price. Secondly, we calculate the environmental impacts using the life cycle assessment methodology. And after, we can we define monetary valuation coefficients. That is a cost of mitigation or repairing the damages caused by the specific emission. For example, for CO2 emission, the climate change, the country should spend a bit more to mitigate the issues caused by climate change. So when we define this value, we multiply by the quantity of emissions, and we obtain the external cost. This, in the first step, we introduce to the sale price. For doing this exercise, we perform a case study in Australia in 3 scenarios: national scale production, regional production, and the local production with the ammonia in a radius of 30 kilometers. For each of the scenario, we define a different technology according to the capacity. Example, for a demand of 1.6 million tons per year of ammonia, traditional Haber-Bosch process using natural gas. For regional distribution, we implement the high temperature plasma for methane pyrolysis. These two options supplied by traditional from the Australian grid, the electricity, because the amount of electricity needed to supply the regional plant is too big. There are no solar photovoltaic farms or wind farms enough. But for the small plant, for the local plant, we can provide electricity with solar photovoltaic. And we use for hydrogen production the electrolysis PS unit for the nitrogen, and the use reactor. We have to consider that for the synthesis in the plasma reactor, we consider the maximum energy yield currently in literature is 30.7 grams of ammonia per kilowatt hour. That means is 28 kilowatt hour per kilogram of ammonia, which is equal to a 19% energy efficient of this process. Consider also the low concentration of this synthesis, which require extra energy for the recycling loop and for the separation. So at the end, we have a overall energy section about 17%. As example of the regional plants, there are already some implementation of the high temperature plasma. This plant can produce up to 300 of ammonia per year. And for the non-thermal plasma, we have the first pilot plant in Australia. Was implemented in a farm to produce wine in South Australia near. And for transportation, it's important to add that we had to perform a specific modeling for both for the cost, of course, and for the environmental. And we in the initial calculation, we use the genetic data from EcoInvent, the most well-known database for life cycle assessment. But we found that they have the genetic data for transport, consider chairs or in different size of trucks, also different load factors, average load factors for transporting normal goods, but load factors in the ammonia are lower. Also, we noticed that the EcoInvent consider the control emissions technology in different trucks, for Euro 3 standard and over, so Euro 4, 5, and 6. But most of them are older. So, for example, rigid trucks, most of them are Euro 1 or pre-Euro. Unarticulated trucks, most of them are Euro 3, and Euro 1 and pre-Euro. That means the specific case for transporting in Australia has more emissions, pollutant emission, and also different consumption. For the reason, because as I mentioned, EcoInvent has calculate the emissions considering the European driving conditions. But in Australia, we have different speeds, different slopes or gradients. So we divide in different sections the main route from west to east Australia and obtaining more accurate results. And the results were changed over the increased by 20% in both the cost and in the energy consumption, the diesel consumption. We have more accurate results here. Each of different trucks per ton kilometer transported. And these are the results for the economic analysis. We can see, sample in purple, the transport has an important contribution in the sale price, the minimum sale price that we have in Australia. So it's about $200 due to transportation. And this is considering the best supply scenario. That is 1,800 kilometers that have to be transported. 4,000 is considered by train. The train is the cheapest, much cheaper than the truck, and only 800 kilometers by truck. And even the best supply scenario, we have important contribution. However, even including the high share of the transportation cost is much cheaper than the other options. It's considered as well because electricity, we consider that is conservative. I have seen on other studies using cheaper cost of photovoltaic electricity, but we have this cost. So currently are not competitive these plants, but if we consider a future scenario, we have seen some studies that says that in the future, the energy efficiency of plasma reactors can increase about 25 times. But however, even in this scenario, the production cost cannot compete with the traditional way of making ammonia. It's important to mention that even we increase a lot the efficiency of the plant, we have still a high production cost, but in this case, about 80% of this blue bar is related to the electrolysis cost, and less than 20% to the synthesis in the plasma section. For that reason, maybe in the future we consider further increasing the energy efficiency of water electrolysis can be more competitive. But now we only focus on the plasma synthesis. Regarding the life cycle, in this case, the plasma plants, they are more competitive. They have much lower carbon emissions. We focus only in carbon emissions to make more simpler this analysis, this graph. And surprisingly, we see the regional plant using high temperature plasma has much more carbon emissions, even much more than the conventional plant. But it's because we consider the electricity here from the national grid, from the Australian grid. There in Australia, most of the electricity is produced from fossil sources like coal. So for that reason, this plant uses more electricity than the conventional one. This is gas, but is worse. So the result is, according to the country, can change a lot. Another thing is we consider here the credits. We have the sale price in this point because we benefits of selling the oxygen in the electrolysis based plant and the carbon black and the steam. Now, for cost, we have to identify the specific monetary valuation coefficients, because the cost of mitigation of the damages caused by a specific environmental impact will be local, depending on the country, depending on the willingness to pay. There are different factors to define how much is each kilogram of CO2. So because we are not reporting specifically, so we decide to use a range, the minimum value in literature and the maximum values. And so our external cost will be in between this range. The quantity of the emissions in each scenario, and we have the sale price after internalization. We can see these prices in this chart, and we see that if we tax with the maximum coefficient, the ton of ammonia can cost around $2,600, but even though it's still lower than the plasma plants. So it's important that we consider only solar photovoltaic in Australia, as a previous presenter mentioned. The wind is is cleaner. The production of the solar panels has a lot of carbon emissions, mainly during the extraction of silicon for the solar panels. So, but the wind energy is much cleaner. But in Australia, we had to use the solar because the wind energy is not as efficient like a solar. So, in another country, we consider the use of wind energy instead of solar photovoltaic. The results can be different. If we consider the future scenario, considering the negative emissions that we have, because the sellings of oxygen can be possible in the future scenario, but the results can change, of course, if we use wind. We have further reductions in the consumption of electricity in the electrolysis part. Also, we know that taxing in this way an industry to make the sale high is not realistic. So we can use this external cost calculation to estimate how much is the annual cost related to the industry. For example, we have an annual demand of ammonia in Australia is 1 million tons, and they represent that the country has to spend around $5 billion in mitigation, repairing the damages of climate change. And if we consider other environmental impacts like ozone depletion, particulate matter, and acidification costs, the external cost can increase to around $6 billion per year. So we can use, or the countries can think, okay, we cannot tax can affect the competitiveness and the exports of this industry and reduce the income the country, but we can invest this money to promote the replacing of the traditional way to produce ammonia and investment for future, because we can save all this money per year. Okay, we can conclude that the plasma in Australia currently, the cost is around $2,400 per ton, and in the future $800 per ton. But further reduction can only happen if water electrolysis increase his energy efficiency. Also, we identified that the supply chain in Australia generates up to 3 tons of CO2 per where 30% is about road transport, and so this decentralized production can save around 900 kilograms of CO2 per ton. By internalizing the environmental cost, the traditional way of producing ammonia can cost $1,600 per ton, but tax high environmental taxes will impact the conventional ammonia industry competitiveness and exports. But we can use that, the total external cost of around 5 billion can be not ammonia production. Okay, thank you so much for your attention.
Okay, thanks, Charles. And any questions? Okay.
Thank you so much. And, you know, getting this Australian perspective, I'm just wondering also in the preceding talks, when you assess the entire impact, whether anybody concerns the water source for the electrolysis for the, or, you know, have steam reforming as here. I mean, we have included the methane or natural gas costs and environmental burden. Now, there's another question. When you do the electrolysis, of course, there is either seawater that you have to transform into, you know, the usability of that, infrastructure costs, and so on. And on the other side, water is also a precious resource. And if we have desert areas where we put big solar farms, water is a concern. So I suggest water costs and the water technology would also be useful, because then whatever product you make, between, you know, hydrogen is the start, and whether you make ammonia for it or from it, or methanol or whatever, in the future, the step from the electrolysis with renewable energies to hydrogen should be figured in the same way. That's my first comment. Second comment is, what may be also interesting is to look at the consumer or side. So what we evaluate now is technologies, and there are countries like, you know, let's say China or US or Australia, where you can try to be self-sufficient, self-sustained with some of these. If you put yourself in the perspective of Japan or UK or whatever, you know, I'm not to say Germany, it's a different beast, because you will be dependent on these sources. Now, if for, let's say, a UK consumer or Japan consumer, to factor out is when you get it from Qatar, you know, the best way economically and environmentally would be too. But if you take, you know, from Australia, so it may also have whether you use hydrogen, dependent on where it comes from, whether you use ammonia, dependent on where it comes from, and so on. So I suggest that to calculate a balance on the perspective of a, let's say, non-autonomous consumer, that may be also a valuable perspective.
Okay, thank you so much for your comments. Related to the first question, the water is a category that myself I have made the same question myself in my studies, because it's very important, but we usually remove the water consumption from the life cycle assessment, because nowadays the database and the software dedicated for life cycle assessment is not precise or not accurate in the analysis of the water, because the water is very local. So, and depend of the demand, the pressure in the water resource. So if there is a lot of demand, low availability, so there are some factors specific for each country, each region. So in the generally used for life cycle assessment, the results actually are not useful. I think we know we cannot rely on the results. So we usually in life cycle assessment, in any of the process, we remove the water analysis. But yes, it's very important. We need data. We need also databases related to the. Some countries they have a lot of information for that. But yes, it's something that is very important to consider when we use the water electrolysis for this analysis. And regarding the autonomous production, yes, many countries try, even after COVID, we try to be more self-sustainable. But yes, we need to also with the geopolitical relationships, we need also we cannot block imports of some products completely. We need to have an open door for imports of the different products, because we can from 100% from imports or 100% of local production. We should be open for all this kind of relationships. But yes, of course, there are much more benefits of local production for knowledge transfer to communities. We are trying to implement also these technologies in the rural areas, because it will bring development to these regions, more knowledge, also decrease cost, related positive influence.
And okay.
Let me try to follow up on this. So when you say the cost of water, the water desalination for the electrolysis is, you said you need more data, basically. What I didn't get is, now when you build your life cycle inventory, and I think you used the CoInvent database, right? So is that in any way included, that you have chemical waste after desalination, that the salt has to go somewhere, it's usually pumped back in the ocean? Is that in some way included in the eco, or it is usually not included?
No, in this study, we assume for the cost, we consider the cost of deionized water, but available from fresh water. And regarding the answer that I did previously was related to the economic analysis, that we have to calculate not only the availability, and it depends of the different data that we don't have in the SoAE for life cycle assessment. Yeah, exactly.
Other questions? Okay. Then, Joss, we have one certificate for you.
So this half section is closed. Let's enjoy the coffee break.
For the ammonia application, recent advances in experimental flame stabilization, pollutant emissions of turbulent ammonia and blended ammonia flames by the Dr. Ayman Alves.
This one? No. This one? Yes. Hello, good morning, everyone. This is Ayman Albas from CAUS. Today, I will titled of towards ammonia application and recent advances, experimental flame stabilization and blended ammonia flames. So I will start with brief introduction about, and then through literature review on single swirl burner fired with ammonia or ammonia blended. Then I will introduce the co-combustion concept of ammonia through swirl and large in my talk with the conclusions. So as we know, to reduce the burning velocity, and in the flow velocity, so this leads to turbulent mixing reduce flame. This is also when ammonia combustion, and the other issue with the ammonia, we are confirmed from burning of ammonia. So we need different strategies to stabilize ammonia from one side. At the same time, we would like to minimize NO emission. This has been reflected in the recent work on the ammonia. As you can see, most of the work emissions coming from the ammonia and ammonia stabilization. And if you are talking about the configuration of the burner, majority of the work are talking about single swirl and then jet ammonia flames and two-stage combustion. We know that ammonia with more reactive fuels like hydrogen and methane improve the flame stability. And the methane followed by hydrogen ammonia plant. So this swirl fired with the ammonia using single swirl. This study show that combustion between the ammonia and methane flame appearance is and so help in preheating the pace of the flame and then stabilize the flame. Once you increase the bulk jet velocity, these side recirculation zones start to disappear and leads to the flame to blow out. This is some results regarding the equivalence ratio for the flame stabilization. You can compare between methane and ammonia. We have a no for the stability of the ammonia. And as you can see, roughly the rich and lean blow in flammability limit of the ammonia. And regarding the NO emissions and unburned hydrocarbons, in the and we can say have the same order of magnitude between the ammonia NO and the NA. So to move forward with the application, this study also showed that ammonia turbine of 50 kilowatt using non-premixed ammonia using this multi temperature, and this plot showed the effect of the and ammonia PM. So they have to use SCR to reduce the NO emissions coming from these burner flame. The follow-up of this study, we can see here the inclination angle of the jet of the ammonia here. They found that if you increase the injection of the ammonia, the flame stability is improved, and this is a comparison between, and you can see the equality of the ammonia is parallel to the axial of the burner, the flame start to be left off. So increasing the important stabilization. And regarding the NO emission, for 45-degree angle show the temperature once you introduce the jet of the ammonia inclined to the in the exhaust. And the ammonia, this study showed that compares a different strategy of ammonia to hydrogen. If you, they showed that if you introduce ammonia based on non-premixed, and this ammonia is burned in premixed hydrogen from outside, this is we called non-premixed ammonia. You can see the NO emissions start to decrease relative to fully premixed ammonia hydrogen flames. 1.2, all of the modes of the combustion start to give almost the same NO emissions. And in this study, the NH2 star as a marker or a good marker for NO consumption in these burners. And for the NH3 CH4 for the heating value coming from the ammonia from 0, which means we have anything compared to non-premixed. We are talking about if you increase 2,000 from the blending of ammonia with methane, very high NO emission coming from this configuration. And they reported that the N2O start to be formed when you go to the lean side. And they highlight the importance of HCN. HCN start to be formed for the rich side in the flame. And we know that HCN has this NO as well in the flame, maybe higher than the tendency of the ammonia to produce to start to be formed for the rich side of the flame. Are fired with NH3CH4 flames. In this study, we explore wide range of effect of equivalence ratio and blending ratio in non-premixed ammonia methane flame. Here, this is the jet velocity and the axial air velocity, and we introduce the swirl. So from 0, which means pure methane, up to 85% ammonium, we present the flame stability. You can see the jet velocity of the fuel relative to air velocity. There is jet velocity and the air velocity. Once you increase the ammonia percentage in the mixture, the sensitivity of the jet velocity to the air and the effect of the swirl number to improve the flame stability start to decrease. Up till 75 limits collapse on the same figure. Further increase in the ammonia, we can see opposite effect of the swirl. So in this case, we reduce the flame stability, and we notice that there is some of go to 50% of the ammonia. Also, we report some NO emissions were not 8, 2, and 12. We conclude that these relative to start to be decreased once you increase the swirling number. And we recommend if you are working on this equivalence ratio and the higher swirl number, we can minimize the NH3, unburned NH3 in the exhaust. At the same time, we can get some lower NO emissions from 0. And this is just show the variation in the flame structure and the NO formation. Regarding the blending ammonia with more reactive fuel, it will produce higher NOx emission using OH and OH radical in the same vicinity of the ammonia. So this is in while we are dealing with the ammonia. And this is just to control the primary equivalence ratio. So we need to control the O inside the flame. And this work has been done issue, you can see the NOx emissions in the primary case is very high. Once you introduce or inject the air in the secondary stage, the NOx start to be reduced for the lean condition. This is maybe due to the dilution effect of the air you are injected in the secondary stage. But for the reach condition, you can see here start to be slightly increased once you go far reach primary equivalence ratio. And this is maybe due to the H2 formation, CO formation. H2 and CO maybe leads to before the secondary stage injection of the air, and then HCN and slightly increase the NO emission. The same thing we produce leading gas injection has the dilution effect when you are talking about the primary equivalent effect when we just proceed to the rich side of the primary. Based on three, we are still need to develop flame stabilization mechanism while we are minimizing the NO emissions. So we need to optimize the combustor design and also optimize the fueling strategy. How could we introduce the fuel together inside our combustion? At KAUST, we are working on the project to investigate the co-firing concept using KAUST double swirl burner. And in this next slides, I will on this concept. You can see here, this is the KAUST double swirl burner. Here we have two coaxial body of 5 millimeter, and we are using a square quartz window to facilitate the optical access to the flame. And in the outer stream, we are only and air, while in the inner stream, we are introducing ammonia air mixture or ammonia. To investigate this, what we did in the last, we fixed the changing the ammonia percentage in the inner stream from zero ammonia in the inner stream, while the equivalence ratio of the inner stream vary from far lean 0.2 to 1.4. For the outer stream, which is methane air mixtures, we fix the number at 4,350, while we are changing the outer stream equivalence ratio from 0.4 to 0.7. We keep it lean. So equivalence ratio under this condition of the flow is still on the lean side. So experimentally, what we did flame stability, measure NO and NH3 emissions, and then we did some in-flame measurement in temperature field. We get the variation in the flame structure. So this is the stability map for the double swirl. Bottom you can see the effect of the outer stream equivalence ratio 0.4 to 0.7. And versus phi n. You can see we have a flashback boundary and flashback to being of the ammonia in the inner stream due to low reactivity of the ammonia. So at this point, flashback. If you increase the outer stream equivalence ratio, these you can extend the percentage of the ammonia you can introduce in the central region, and at equivalence ratio of 0.7, we don't have any lean flow out limit. So the flame is stable, and you can introduce 100% ammonia inside the flame. And in summary, this is the flashback region. The flashback region was insensitive to the outer stream. And this is the lean flow out limit. You can see increasing the outer stream equivalence ratio leads to reduce the flow out, the flame stabilization. This is just to show that the overall equivalence ratio is still in the lean inside stream equivalence ratio from 0.6 to 0.5. It shifts the blowout limit to lower values. the and as you can see, increase the ammonia in the inner stream to 25%. We have increasing in 75% of the ammonia in the inner stream. The NO emissions start to increase. Once you go back to 100 here, we have a steep decrease in NO emissions up to equivalence ratio. Once we have a slightly decrease, the effect of enriching is the effect on this tube. Decreasing the equivalence ratio from 0.7 to 0.6. This is very sensitivity of the NO. Once you increase the decrease the equivalence ratio from 0.7 to 0.6 to 0.6, here you can see a higher NO emission start to be produced from the burner. This is show the high sensitivity of the NO relative to the outer stream equivalence ratio. And with we increase the outer stream equivalence ratio, we will have reduction in NO emissions like greater than 0.7, but back for the outer stream here. So the analysis of this result maybe in ways we can find it here. If you increase the XNH3, the NO emissions start to increase up to a certain value. After that, the NO start to decrease because we have a reduction in the radical pole of OH and OH. However, the further increase the NHI radicals, it will be also decrease, and this is show the sensitivity of the NO inside the flame up higher than XNHC greater than 0.1. We can see relative to the free radicals of OH and O. 100% ammonia. This decrease a little what we observed here in our NO emissions. To do some inflame measurement, we decide to go with 100% flames, and then at 0.8 flames and far lean flames. This is the first set. Also at 50% of the ammonia inside the inner then you can set up reduce the reach to 0.6. This is to understand the flame structure and the variation in the flame structure. This is the flame appearance. You can see here, this is 100% ammonia inside the flame with lean inner stream. Equivalence ratio. Once you go to 50% of the inner stream methane, the flame becomes shorter and become more intense in combustion as it appears from the flame observation. So for the temperature field, again from left to right, we have flame with far reach, and then flame lean condition at phi in 0.8 and far lean. You can see from flame 1, 2, and 3, the temperature start to decrease once you go to the far lean and very low temperatures. However, you can see the NO emissions 250 ppm relative to 200 ppm. And this is explain how much if even for the lean condition, if you hold is ammonia, it will trigger higher NO emissions. And the effect of XNH3 0.5 start to increase the temperature of the flame overall and increasing temperature. This is the case where we decrease the outer stream equivalence ratio to 0.0 region of low temperature, but still we have very high far reach flame 1.4. So we decide to do the OH plef in these flames, and this is the configuration from far reach to far lean. We have a conical shape in OH radicals start to be formed, and this is owing to the outer stream methane mixtures. Once you increase the equivalence ratio to 0.8, we have broadening in the OH radicals and engulf the air and the ammonia from inside, and this is increasing the formation of NO. And interesting, what we found here in the far downstream for the far reach start to be formed as this layer start to be formed. This may explain the why when you go to the far reach, the NO is fine. And this is again if you introduce some the center, the OH layer becomes higher and higher, and then increasing the NO emission. To decrease the outer stream equivalence ratio, you can compare this case and just to decrease the outer stream equivalence ratio of 0.6. And this is increasing the NO emissions to higher value when you this I will do the mental part. So for the flame stabilization, increasing XNH3 will modify the flame stability, increasing the lean flow out limit, and narrow the flashback region. Increasing the outer stream equivalence ratio enhance the flame stability, whereas the flashback region remains unaffected by the outer stream equivalence. Regarding the NO emissions, low NO emissions were achieved at 100% ammonia within the inner stream by either the flame or far leaning out the inner stream, while we need to have a precise control of the phi out, of the outer stream equivalence ratio. At phi n greater than 1.2, when you go to far reach of NO reduction by reaching phi n decreases and increases with XNH3 slightly. We have OH left showed a conical OH layer at the burner exit. At certain conditions, formed beam. Right? We did the LES for some cases in the double swirl burner and Okafor mechanism for this LES simulation. So we decided cases where we have 100% ammonia in the inner stream from far reach 1.4, 0.8, 0.2. This is the experimental results. Here, this is the NO emissions, and this is the NO predicted NO. Yes, but we did some 1D simulation for the 5 mechanism. We mixed mixture, the solid lines. This is the solid lines. We assume the methane and the ammonia are fully premixed, and this is the NO. For this dashed line, we assume we switch off the out flames, talking about 100% ammonia without supporting coming from the outer stream. Here we can see that the double swirl burner improved the flame stability to far reach relative to ammonia flame. Also, if you compare the the double swirl, we have a reduction in NO emission around 90% reduction in. We will see the flame structure for the OH be formed in the inner boundary of the inner wall of the good matching between the that showed here from far lean to far rich flames. So we did some we conclude that the OH radicals from the outer stream CH4 could interact with the ammonia flame in the center to form NH2 and NH. And in NH we can take it as a good marker for the reaction of ammonia flame. This plot showed the NH3 distribution from far lean to far rich, and here this is the NH4. We have a thin NH layer start to be formed, and the mass fraction of the NH start to be increased. You are in the equivalence ratio, as we can see from left to right here. And we noticed that the increasing intensity of the OH along the central reaction zone relative to when attributed to the formation of hydrogen to trigger the formation of OH in this. Understands the mechanism of double flame interaction. The flow field here showed that we have two corner recirculation zone. This shear layer triggered in mixing. Can it change the mixture fraction of the ammonia along with the combustor? And we can see that Z here is defined as the mass fraction of the ammonia relative to the mass fraction of the ammonia at 0 outer stream to 1 for the inner stream. You can see the distribution of the side, this one. This help us to understand there is some interaction the oxygen from the outer stream can introduce to the inner stream. This is the mechanism between the two streams. And NO form, you can see here. This plot shows the mass fraction of NO and N2. Here is NO for the three flames, and this is the N2O for this flame. And their formation and the consumption rate. The consumption rate in blue and the formation in red. You can see the NO is consumed mainly in the preheat zone of the ammonia flames through the interaction with NH3. So and after that, so this is why we did not see NO in the preheat zone upstream the NH layers. And for the HNO, the main mechanism for forming HNO reaction, you can compare the HNO distribution with the NO distribution inside the flame. The N2O, you can see for the formation and consumption that the N2O start to be formed earlier in the downstream of its formation layer. And if you look to the case where we a lean condition, we have a very weak NH layer start to be formed here, and it shows a significant increase in emission. And if you compare the NO and N2O, you can see the spots where we have a higher N2O. This means the main mechanism for formation is NO formation. And also, we need to be into the preheat zone. Okay. Conclusion remarks regarding the double swirl burner, the novelty of the double using two swirlers, with the outer methane stabilizing the inner methane. NO emissions by ESP burner compared to fully premixed case, alongside significant in case where we have phi in 0.2 stream stabilize the inner flame and to contribute to NO. The outer layer with the inner mixture decreases the NO of mixing of products from gas from the inner and outer flames downstream reduces the NO and N2 emissions in the exhaust. This is some future work we are doing now in the Gauss double swirl burner. So we are investigating to increase how the effect, since the issue is mixing between the two streams. So we are trying to increase the Reynolds number of one of the streams to see the effect of this Reynolds number on the NO emissions. Also, we are reporting some recently some data regarding the NO, the Gauss double swirl burner, and the future work we will both the double swirl burner to investigate that in our high pressure combustion duct to investigate the effect of the pressure on the emission and the flame stability of the Gauss double swirl burner. With this, I would like to thank all of the people contributing to this work. This is our team and the sponsors. And thank you for listening, and happy to answer any questions. Thank you.
Thank you for interest. It's open for the audience for discussion. So any question or comment?
Thank you.
Thank you.
And I have a question regarding the two double swirl burner. We did a two-stage burner. Can you tell advantage, disadvantage of these two?
Question, and of course, by you are the co-author of this work. So anyway, I think the combustor design is very compact. So I think it used between the outer stream and the inner stream reduces the NO emission, and this is the target. The issue here is if you would like to make a compact combustor of the performance. And it gives us, like, if you go far reach, we have some slightly increase in the NO, and I think we found this in the stage of combustion as well from the group of from Japan. They show the increasing in NO once you go to far reach flames. But I think the simplicity will be one advantage of this burner.
Okay.
Yeah. According to my understanding, in the double swirl, you separate the full stream in inner ammonia and outer methane. So the fuel is not mix extra supply of OH to the ammonia. Therefore, fuel NO emission is reduced, and in the main flame there's a thermal NO. So did you quantify how much from fuel and how much from, because when ammonia methane are mixture, it's completely the fuel NO, but in your double swirl for the fuel NO and thermal NO outer layer. So did you quantify in your LES simulation?
Yeah, I think the experiment we did some methane flames inner and out, and we saw This is emissions was very low relative to when we introduce ammonia. And for the LAS here, and in this plot you can see the very high NO emissions. We have different mechanisms, so the different mechanisms give you at the far reach flames. You can see the fully premixed flames with ammonia methane. The cows will go to the 100% ammonia in the inner stream.
Include how to separate fuel NO and thermal NO.
This is one dimension.
Is now already published. We can quantify thermal and NO.
Okay, thank you. So it's time to finish this talk. Certificate.
Thank you.
So the next is a invited lecture. So Dr. Whaley. So the title is the towards methane equivalent thermochemical properties steering system for gas turbine applications.
Good morning, everyone. My name is Wei Li from Shanghai Jiao University. My great honor is the work on the methane equivalent thermochemical properties in ammonia co-firing. This is outline as know and power is critical for the sustainable development. This factors the adoption of zero carbon fuels, particular ammonia and high electricity is one of the most promising ways. Fuel statistical of various combustors. This would need of from significant fuel are very promising fuel in the gas turbines, marine engines, and flights. In China, annual ammonia production critically reaches up to about 60 million tons. However, challenges remain in the combustion utilization due to the high energy consumption in synthesis, pollutant, and also the lower combustion reactivity. Among these issues, the lower reactivity requires focused attention. Fuel co-firing is a commonly used strategy for ammonia combustion. The co-firing fuels need to be carbon neutral and compatible. For compatible, the thermochemical properties include including the large valve index and the laminar flame speed, need to be matched to the common fields such as methane in gas, and the volumetric value is an important indicator in designing the terms of gas fuels, and the valve index is a significant indicator of gaseous fuels character, and with fixed geometry and pressure drop, and the laminar burning velocity combustion stability. So how we can achieve the significant carbon neutral fuels with methane equivalent thermochemical properties? If we start from the initial compound ammonia and 2 is of equivalent to those of methane, it is essential to consider the utilization activity such as hydrogen and the fuel with the high specific acetylene to butane all exhibit high thermochemical properties. Solution calorific to the first system calorific value system, and in the renewable gas fuels, it has the higher heating value and the renewable in the proportions of ammonia, hydrogen, and DME, and that are similar to those of methane, as indicated in the red line experiment. We choose the 6 components F1 to F6. The content of ammonia is hydrogen is increased, and the maintains a volumetric heating value similar to that of methane, but we can notice that their Bob index was gradually increased. And this is our apparatus. We use the constant volume combustion vessel to investigate their laminar burning velocities. We also developed the kinetic models, and these are the performance of models for the pure fuel, dual fuel, and the tree fuels. This figure shows that F1 to F6, with the increase of the hydrogen, the laminar burning velocity is increased. And we can see that under these conditions, the laminar burning velocity can achieve at the value of enhancement. We use the updated Fichtinius dilution gas. By using this way, we can separate and both from the F1 to the content of these reactive radicals was in both the thermal and chemical effects are contribute. as a fuel on the state of mixtures. We introduced a factor, we call it the LPV variation coefficient to evaluate the effect of this normalized laminar bending velocities to the averaged value. And we can see the result that this is the MECV system, and this is the ammonia hydrogen system. We can see that higher than the tree fuel system. We calculate the contribution system. The contributions of DME contribute to over it's very important for DME in enhancing the laminar properties. And if we normalize the MECV, we can notice that similar to those of the ammonia and hydrogen. The roles of the DME. DME has the bell-bust effect of this comparison fuel system with methane. We can see that the laminar bending velocities of F1 and F3 is much similar under these most conditions with the methane. Further, we also perform the swirl flame characteristics. We use this gas turbine model combustor and some diagnostic methods to give some diagnostic of the system. And we can see F2 and F3 mixtures behaves much likely to those of but we can see that in this system, we cannot capture the Bobble index. Well, this factor is very important in the gas turbine applications. So the work is about the simultaneous regulations on the calorific value and the Bobble index. To better produce the thermochemical properties of methane, high calorific value and Wobble index has been elected in this. According to the recent investigations, butane can be produced also stocks, and it is also a major component of the liquefied petroleum gas. As to ammonia and hydrogen, this requires the minimum especially in the marine and also in the automotive transportation. It's possible to realize the calorific value. This is the crossing point in this finger. Accordingly, we also performed the one is FB. For FV, this series is to match the heating value, and FB is for the Wobble index, while FV5 is the cross point, which can both satisfy the MECV and MEWI. For each series, we can notice that with the increase of the member, the ammonia concentration is gradually increased, while the butane content changes slightly. We also simulations, and the one model published in 2022 can better capture the experiment. The analysis was performed using these kinetic models. We also validate the other models, and the one detailed model can better capture the experiment. The two figures shows that the measured and simulated results of these mixtures and MEWI conditions, and the blind samples is the result of meshing. It can be observed that both EV and MEWI conditions, the laminar bending velocity shows an increasing trend from, meaning that the mean as the ammonia concentration. So by co-firing with a built-in, achieve the laminar bending velocities of this fields. Furthermore, based on the improved the enhancement mechanism, and found that under the condition the adiabatic flame temperature peak is more certain or mass significance. So the analysis of the combustion ammonia, both hydrogen and unbuilt-in, more readily to reproduce the hydrogen atoms. This initiates the crucial chain branching reactions. We call it the hydrogen plus O2 to produce hydroxyl and oxygen, which promote the formation of other reactive radicals, such as O and OH radicals. These radicals role in the reaction network of the three-component mixtures. Furthermore, the analysis of the thermochemical properties revealed that the value and wobble index, we can see these fingers. It has a linear with the component. Well, the laminar bending velocities exhibit the non shows a very steep-clipped behaviors near the hydrogen peak. They exhibit a more gradual slope. Then, binary fuel mixtures are also performed, and we can see that all the five conversion curves exhibit a very upward trend from ammonia to unbuilt-in banded from these fingers. Well, the other this is attributed to the changes fuel and also the wobble index of this component. It can compensate for the conversion variables. It was found that the conversion variables compensate for the heating value gradually can constrain the conversion curves while resulting near square relationships. But for the complexity of the warp index present challenges in the considering these curves of the hydrogen, especially for the hydrogen blended mixtures. But for the conversion from ammonia, the conversion can be fully linearized. Similar, we also perform the calibration of the fields. We can see that this is the comparison of the ammonia built-in system. We can see that they have large difference, and we use the same method to calibrate by using the LBV variation coefficient, and the result shows the ammonia hydrogen has much higher value than the tree field system, and the contributions of the built-in can up to the system, and we also calculate their normally that this value are also very close to the ammonia built-in also act as a very high specific component trigger calibrate value. Similarly, we also it can also be observed that replacing the and enhance the fuel reactivity and the flame stability from FA1 to FA5 and from FB1 to FB5. The flame anchored position shift upstream and their structures are become more compacted. The chemiluminescence is also enhanced. The lean extinction limit are also decreased, so it denotes that their combustion stability are significantly improved. The cell can see that it's of FA3 and FB3 to FB4 are much similar to methane, while the lean burning limit of FA2 and FB2 are values of methane. Comparison with methane, FA achieve the methane equivalent heating value and warp index conditions, but because concentrations is as high as the 0.65 concentrations of hydrogen, so its laminar burning velocity is much higher. We can see that it has 2 to 20 higher than that of methane. So this indicates in the using hydrogen in the methane equivalent heating value system and hydrogen built-in electric system can significantly increase the reactivity comparable to that of methane. Further considerations is also needed in the fuel mixtures. And last is the conclusion. We performed the MECV and MEWI conditions for properties of the ammonia, and there is a very urgent need to develop knowledge to for these fields to achieve the this would enhance the usage of these fields in the extensive mechanical modification. Thank you very much. This is the end of my lecture.
very so audience. Okay. If not, may I ask?
Yeah.
So you measure the frame speed for various mixtures, but how is the maximum length? If you use the spherical frame, right?
Yeah.
So the maximum length determines at the same time.
Yes. Yes, we measured the laminar bending velocity, and also we can obtain the maximum length of this system. Yeah. And we didn't show the maximum length in our slides, but we observed that the maximum length it behaves much like the such as it has the equivalence ratios, not like the ammonia and the hydrogen. Yes.
So that it follows the trend of race number.
Yes.
Okay, thank you. So,
Thank you.
Are there any comment? No. Okay.
Thank you very much for the nice presentation. That you are as a ballast to regulate the properties of these. So just one simple question: how is DME being produced? Because you say 80%, a lot of DME for that. So how is DME going to?
Thank you for your question. Actually, for DME, the renewable route to produce it by using the hydrogen and the carbon. Yes, and maybe it's missing way, and nowadays maybe it can use other.
Okay, thanks. So it's time for lunch. So we